we're going to do the second part of the lab. It's so nice to see you. Okay. So everybody is going to get their elements. And we are going to see if these elements are in the stars. I need to get one more. So rip them apart if that's easier for you. And you're going to line out first hydrogen. Let's just clarify that yes, hydrogen is in the sun. And then see if hydrogen is in any of the other stars. So rip it off. You're not going to be keeping them anyway. Unless you want to keep them to practice for the exam, you can. But you are going to take your piece of paper and you are going to line it up with the sun. You're not going to put it on top of the sun, but you're going to line up one end on one side and then the other end on the other. Obviously, mine is not to scale. And you're going to see, okay, do the bands of missing light, or does the absorption spectrum of hydrogen match up with the bands of missing light in the sun? Then you're going to move down to procyon, or procene. I'm going to give us 8 minutes on the timer so that you can do that. And then after 8 minutes, let's go out and share out our results. That one's good. Yep. Even though it's got that little line in there, it's just on the inside of that. So for those of you at home, we just reviewed what we did for the first part of the lesson yesterday. So if you need to go back that and check it, go ahead and watch part 1 of the STAR Lab. This is going to be part 2 of the STAR Lab. We're starting with our absorption spectrum of stars and elements. If you need help, if you want me to come over and check to see if you're doing this accurately, put your hand up and let me come, please, and help you out. Elijah, that one's good. All right, I'm going to take attendance really quick, so if you need me, I'll be over in just a minute. Has anyone seen Enzo this morning? Thank you. know we have about 4 minutes before we'll check our work. If you're totally completed and you want to turn and try to get started on the next part, you can do that. And then when we are ready to check our work, we'll all come back to the table and check our work and then move forward together. But if you're ready to move on, you can try to move on if you want. If you want to wait, then you wait. About 40 seconds, and then we're going to check our work on this portion. I want to remind some of you, there we go. I want to remind some of you that our vocabulary quiz is still out there waiting for you to get into. If you could please go to this past Monday on the Canvas and then click on that link. Use your vocabulary sheet that we handed out 2 weeks ago as the word bank. It was handed out on, I believe, on maybe the 19th of October. So if you need to go to past calendars and get that information, please do so. Let's check our work. All right, let's go ahead and go through the sun. We know that the sun has hydrogen in it. Can someone tell me, does the sun have helium? Yes, so we're going to check that off. Does the sun have sodium?
Yes.
Yes, thank you, man. Magnesium?
Yes.
Yes. Oh, calcium?
No.
No. Put an X in there. Iron?
No.
No. Let's go on to procyon. Does it have hydrogen?
Yes.
Yes. Helium?
Yes.
Yeah. Sodium?
Yes.
Magnesium?
No.
Calcium?
Yes.
Iron?
No.
Beetlejuice, Beetlejuice, Beetlejuice. This is funny. Does Beetlejuice have hydrogen?
Yes.
Helium?
Yes.
Sodium?
Yes.
Magnesium?
Yes.
Calcium?
Yeah.
Iron?
Yeah.
Woo, Beetlejuice must be a huge star. Does Sirius have hydrogen?
Yeah.
Helium?
Yeah.
Sodium?
No.
Magnesium?
No.
Okay, I'm only hearing one person no. Can I have confirmation that it's actually no? Not that I don't think Carter knows what he's doing, but can I have confirmation, do we not have magnesium in Sirius? Good, thank you. Calcium?
Yes.
Iron?
Yes.
Iron is in Sirius?
No. Huh?
Check it again.
Oh, I will.
Aldebaran. Is there hydrogen in Aldebaran? Helium? Carter, is it?
What? Oh,
in
no.
Sirius?
No.
No iron in Sirius. Sodium for Aldebaran? No, okay. Magnesium? Calcium? Iron? All right, so there we go. With this information, now we are going to move on to the next part. So please turn the page. Now, some of us might find it easier rather than flipping back and forth. If you just open up both pages so that they're both in front of you, that would work really well so that you don't have to keep flipping back and forth because you need the information on both of these pages. So let's go ahead and read about this woman. This woman was introduced to you last Wednesday when you watched the video Sisters of the Sun. And if you've not watched that yet, please do it. You're going to need that information. She developed this classification system we're going to use today. In 1925, Oxford University awarded an honorary doctorate of science to a woman for the first time in history. The recipient was Annie Jump Cannon. That was her. She was an astronomer who classified more stars in her lifetime than any other scientist to this day. You know the computers that you all have? These were the first computers. Okay, so a computer was a woman that crunched numbers, that took numbers and worked with numbers. So the computers we all work with today are due to these women. She developed what's called the Harvard Classification Scheme. It's a way to classify stars based on their spectra, or range of light energies. We still use this today with only minor modifications. The classification scheme divides stars into 7 spectral classes, represented by these letters. I do not know why she uses those letters. So let's go ahead and look at what we are doing on this portion of it. We're going to use the data from your investigation on the table before and this classification scheme to fill in the table below with the class, the color, the surface temperature of the 5 stars that you investigated. So we are now at the classification of stars part of our lesson. The first one we're going to look at is the sun. And I'm going to go to Elijah on this because, Elijah, you weren't with us yesterday, so I want to make sure that you're up to speed with us. Notice up here, these are the spectral classes, and these classes are developed based on what elements are in the star. So could you please look at the star, the sun, on the front side, and tell me the one that you did before. Yep. So we're going to be looking up here. Is hydrogen in the sun?
Yes.
Okay. So if hydrogen's in the sun, all of these stars have hydrogen, so it could be any one of them yet. Is helium in the sun?
Yes.
Okay, so it could be any one of these. It's not going to be an O star because there's no helium in that, but it could be any of these still. Okay, is calcium in the star?
No.
Okay, so I know that it's not an A star, I know it's not an F star, I know it's not a K star, I know it's not an M star. So what is the only star left that does not have calcium in it?
G.
Right, so we know it's a G-class star. So we're going to write down that it is a G-class star. And now, Elijah, if it's a G-class star, what is the color of a G-class star?
Yellow.
Right, so we're going to write that down. It is a yellow star. And the surface temperature of the sun would then be what?
5,000 to
5,000 degrees to 6,000 degrees Kelvin. Fabulous. That is what you're doing with this portion. Please continue to work through that, looking at all of the stars, please, that you classified. If you are finished with this portion, move on to the next portion, please. If you want to wait until we're all together, you can, or you can move forward. All right, let's go ahead and check if we could please to go back to the spectral class. What did we classify or procyon or procyon? Aiden, could you please tell me what's the spectral class of procyon?
F.
What did you say?
F.
As in Franny? As in Frank? Did you say F?
Yeah.
Okay, F as in Frank? I think he's saying yes.
Yeah.
Beetlejuice, what do we classify that as? Riley, could you tell me what letter? N as in Nancy? M as in Marianne? Okay. Sirius, can someone tell me, Nessa, what did we do Sirius as? A as in apple. And then Aldebaran, Ryan, what did we do that?
Okay.
K as in Katie. Fabulous. I am not going to go ahead and then label what the color and the surface temperature are. You can definitely go back and check your work. How are we feeling so far with the first table we filled out as far as identifying elements in a star? Thumbs up like, yeah, I could do this on the exam, or thumbs down like, no, Miss McGrain, I can't do this. What about being able to classify stars based on those elements? Thumbs up, yes, I can do that on the exam. Thumbs down, no, I can't. Good? Great. All right, so let's go ahead and move on to the last section. We are going to look at number 2, which says, which elements appeared in every star's spectrum? Eduardo, which elements were in every star that we looked at?
Beetlejuice.
No, what elements? Not what star, what elements, like the elements that were on the papers that I gave you, which elements appeared in every single star? Was hydrogen in every star?
Yes.
Okay, hydrogen was in every star. And was there any other element that was in every other star?
Helium.
Okay, so we've got hydrogen and helium were in every single star. And that makes sense because hydrogen and helium are the most abundant elements in the universe. They were the very first two elements created during the Big Bang. The atomic mass of the elements from this activity are listed in this table over here. So when we talked about the periodic table last week, we talked about the atomic number, which was the number of protons. The mass is how much total matter is in there. We're looking at the subatomic particles together. So we look at the protons and the neutrons. So the atomic mass of the elements from this activity are listed here, and it is in atomic mass units. So what is the heaviest element? And I hate that word, it should be most massive element, but what is the heaviest element? Misha, for you, could you tell me what's the heaviest element on this list?
Iron.
Iron, very good. So we're going to go ahead and say heaviest. I think I spelled that wrong. Heaviest element. Yes, I did spell that wrong. Heaviest element equals iron. What is the lightest, Aiden? What is the lightest element on this list? Hydrogen is the lightest element. That makes sense. It's got the least amount of matter. The least mass because it's got the least amount of matter. Fabulous. Based on this information, are heavier or lighter elements more common in the universe? We cannot tell from this table, but how can we tell what's the most common, what elements are most common? Not from this table we can't tell. Where would we have to look to find out what elements are most common? The data table of what though? Because this is a data table. Which data table? The element data table? She's pointing us to this table. This table right here, if we want to know what elements are most common, we would have to look at the sampling of stars we went through and see, okay, what elements are most common here? And what did we find out? What elements are in every single star we looked at? The lighter elements. Hydrogen, very light. Helium, the next second light. And they are in every single star we see. So lighter elements are more common than heavier elements. Because the heavier element of iron is only in how many stars, Carter?
2.
Only 2. Only 2. So heavier elements are not as common. So what we're going to do is say, based on this information, are heavier or lighter elements more common? Lighter elements are more common. Think back to when you learned about how stars produce elements through nuclear fusion. Using this knowledge, which stars from your investigation are probably the 2 most massive stars? Which stars are going to be the most massive? Meaning they're going to be able to fuse together the heaviest elements. Every star out there, it looks like it can fuse and make helium. It doesn't look like it's a problem for them to fuse lighter stars. But if we want to go ahead and think about those marshmallows we were squishing together, the more marshmallows you try to squish together in nuclear fusion, the more pressure and heat you need. Well, if you're going to have a lot of pressure coming down on a core, that star better be incredibly massive to be able to smush together those marshmallows, if you will, that we were trying to smash. So, which stars from your investigation are probably the 2 most massive stars? They're the ones that can make the most massive elements. What 2 stars, Carter, make the most massive elements?
Betelgeuse and Aldebaran.
Right, and I can't spell that, so I'm going to go ahead and look here. So we have Betelgeuse. And Aldebaran. And you have these right in front of you, so you don't need to look up at me in case I spell mine incorrectly. Look at the page that you have. This question is for who feels pretty confident in what they're doing right now. Oh, come on, I know you do. Misha, you look like a very competent person. Which star is probably the least massive?
Cyrus.
Which one?
Cyrus.
She says Cyrus or Sirius. Why? First of all, do we have confirmation, yes or no? I have one confirmation. Do I have anybody that wants to disagree with her? No? Okay. Why do you say that?
I do.
Okay, tell me why you do.
I want to say the sun.
He wants to say the sun. What do you want to say?
Procyon.
Procyon, okay. So I've got 3 different stars. Let's go ahead and look at them. We're looking at which one is the least massive. So I'm going to go back to this table. Not that table. This table. I have one person that is telling me this one is the least massive. One person's telling me this is the least massive, and one person's telling me this is the least massive. So now we're going to have what's called discourse. We're going to have a conversation. We're going to have some disagreement. So first of all, Misha, why did you say what you said? Why Sirius?
Because calcium still has less, what is it called?
Mass, good.
Than sodium and magnesium.
Okay, so you're saying
Yeah.
calcium has less mass
Than
Then-
sodium and, what's it called?
than sodium and magnesium? Okay, what else? That's your defense?
Yep.
Carter, what'd you say?
Well, that's not even true.
He's saying that's not true, so let's go ahead and check our data. So, calcium has 40 AMUs, and sodium has 22. So calcium is actually more massive than sodium, and calcium is more massive than magnesium. So,
I'm
you're wrong. We know it's not serious. That's okay. Now let's go ahead and look at the other 2. We have, oops, I didn't line those up correctly, did I? We know it is not this one. So now we've got between Procyon and the sun. So Carter, go ahead and defend yourself. Why the sun?
Because it doesn't have the 2 elements that have the most mass.
It doesn't have the 2 elements that have the most mass. So you're saying it doesn't have calcium and it doesn't have iron. And so, okay, why did you say what you said?
Because it doesn't have the iron, which is the one with the most mass.
Okay, neither does this one.
Yeah, and it doesn't have magnesium.
And it doesn't have magnesium. But it does have calcium. Which one is more massive, calcium or magnesium?
Calcium.
Calcium. So if this one has more massive elements, then we have to throw it out. So when we look at the elements that are in the sun, it has the least massive elements. It's not that it has the least amount of elements, but when we look at those elements, they have the lightest mass. They have the least amount of mass, which means matter is what makes mass, so it's got the least amount of matter. Good. That was very pleasing to me. All right, so the least massive star would then be the sun, B/C, because it has the lightest elements. This means it equals less matter, and matter makes mass. Up here, the how do you know for Betelgeuse, it has the most massive elements. So, it has the most matter. Let's go ahead and look at the last one. Do you think a star's spectrum will change over time? Will the light that it's putting out ever change? Or will it always be putting out the same light? Let's just start there. Do we think that a star's spectrum, or the light waves that it puts out, are going to always be the same? What do you think? Yes or no? No. What do you think? Yes or no? No. Do you think yes or no? Will they always be the same? Yes? No, they will not always be the same.
No?
What do you think? What do you think? What do you think? What do you think, Nessa? What do you think? Emma?
Wait, what star spectrum does it mean, like all the stars spectrum?
I just mean like our sun. Will our sun always be putting out that same signature wavelength of light, or will it be changing as it gets older?
Changing as it
She says it will be changing. What do you think?
Change.
Change? Change? Change. I agree with you. It will be changing. Because as our sun runs out of hydrogen and it can't fuse hydrogen to hydrogen anymore, what's going to happen is it's going to start then fusing helium and helium, or helium and hydrogen. It's going to change into something new. And we saw when we were burning those chemicals, they put off different light signatures. So if it's now creating a different element in its core, it will then be putting out or releasing different wavelengths of light. So as a star ages, what it's fusing changes inside of the star. When a star ages, it changes what it is fusing in its core. And we're going to say each element, this is bringing us right back to the very first section we did. Each element has a specific wavelength of light pattern that helps us identify it. As the elements change, the light released from the star changes. As the elements change, the light released also changes. Sorry, my handwriting is just gross. Does this feel like, wow, this kind of makes sense to me, Miss McGrain? I'm getting this. Sort of a little, not really a lot, maybe, yeah, kind of, okay. How much time do I have, Emma? 4 minutes, 5 minutes? We get out at 40? 2 minutes. What the heck is wrong with my watch? We got like 4 minutes, okay. So that is our time. Did we watch the video yesterday?
Yes.
We did? Okay, so then you've got 4 minutes. What, dear? Oh, we've got about 5 minutes to go ahead and what you want to do. First thing I would do is, my God, figure out where the vocabulary quiz is. We gotta go ahead and get that done. So we've got about 4 or 5 minutes to work on what it is you'd like to work on. Please, if you've got stuff to catch up on, now's a good time to maybe ask Miss McGrain, I can't find this. Where would this be? I need help with that. This is like my opportunity. I don't have a recycling. They're not allowing us to recycle anything. Everything has to be thrown in the trash. So yes, you can throw it in the trash. If you want to use them as a way to practice for the exam, by all means do
I
that.
still have a question on how I tell you right.
For the sun,
Even if you add sodium and magnesium together, it's more than just calcium. And
Well-
we're going for less.
right, we don't know how,
You don't know
okay,
how
so
many
you're just
elements
looking
there
at one, you're looking at one atom and one atom.
So technically it was right.
But you don't know how many atoms there are.
Right,
So that doesn't mean carbon, right?
it is. because, sweetie, if we look at the entire star as an entire system, it's going to have lighter elements in it overall. I could tell you you're right if that's gonna make you feel better.
Yeah.
Okay,